we've finished talking about fields, and if you haven't watched those videos on electric fields, you should probably go back and do that first. But we're talking about circuits. So electric circuits are basically a way of taking an electric field and confining it to a certain path that will allow you to do work using electric potential energy. So the first thing that we need to talk about is current, because current is what's going to allow us to do work in different ways. So current is the flow of positive charge flowing through a circuit. So in physics, the convention is that we talk about current as the flow of positive charge, even though we know now that negative charge is the part that actually flows. Okay, and we're going to talk about only direct current. So that's the type of current that you get when you connect a battery to something. It only flows in one direction. The current you get flowing from your house outlets is alternating current. And that means the direction flips back and forth constantly, a certain number of times per second. So in order to do the math with alternating current, you would need to use calculus, because calculus is the math of change. So we are going to restrict ourselves to direct current, things connected to batteries. Okay, but a lot of these principles will be still applicable to alternating current. It's just you have to do some tweaks. So current is the flow of positive charge through anything. So we said that just charges moving somewhere, that's current. In our case, we're going to be talk about charges flowing through a circuit. So current is I, and it's charge flowing through a certain area in a unit of time. So it's charge, Q, divided by time. Okay, and so I, current, is measured in amps. So that's current, and it's measured in amps. The Q is charge, and it is measured in coulombs. And the time, that is measured in seconds. So in electric circuits, you sometimes had the choice to use ECs, elementary charges, in your calculations as long as it matched your field measurements, your field units. In this case, you don't have the choice. It's just going to be coulombs. Now, we're not very often going to actually calculate the current. We're more going to focus on how current is related to things like voltage and resistance. Okay, so current only flows in a closed circuit. A closed circuit is a circuit that has no gaps in it. It's a constant path. Okay, if you open that path somewhere, you get an open circuit. Okay, this means that there's a gap in it. So a closed circuit has no gaps, an open circuit has a gap in it. And when you have an open circuit, it's not like current flows part way and then realizes, oh, there's a hole in this circuit, can't go anymore. No, when there's a hole in the circuit, you don't get any current flow anywhere in the circuit. And then once you close that circuit somehow or redirect it to a completed circuit, then current will flow again. But in an open circuit, you will not find any current anywhere. Now let's talk about the parts of a circuit. We're going to use schematic symbols for a lot of this stuff because that's how you'll find them in actual circuit diagrams. So first of all, any circuit needs a voltage source. It needs a source of electrons to flow through the circuit. So we're going to make it look like this. Some voltage sources, this is all you get. A positive and a negative terminal, that's fine. Technically, this would be the symbol for one cell in a battery. But most batteries are made of multiple cells, and so you'll get multiple stacks of these types of things. Okay, but it doesn't really matter how many you do. The point is that you recognize that this symbol over here is a battery symbol or a voltage source. So an AC circuit would have a different symbol. It would look something like this. Like that. That's because an AC signal is produced in a sine wave. And so this is the symbol you get for the voltage source in an AC circuit. This is the symbol for a DC circuit. So this is the voltage source. That's part one. And the voltage source provides the potential difference. This is also called EMF, electromotive force. But EMF is just another word for voltage. It's just used specifically in the case of a battery. Okay, so a battery provides voltage or electromotive force to push electrons through a circuit to produce current. You also need some sort of path for it to follow. A conducting wire is what you'll mostly find. In circuit boards, it's not going to be a wire most of the time. It's going to be a copper trace. So here is our conducting wire. Now, I haven't closed that conducting wire because a battery connected to a blank wire will burn out the battery. Okay, that would be called a short circuit. It doesn't use up any of the potential energy that those electrons have going from one side to another. Okay, so it's not going to work properly. So we need a path for electrons to follow. Okay, and the last thing that we need is a load. So the load is whatever you're powering. So when you start at the source over here, that's the source. The source provides electric potential energy to electrons to move them through a circuit. And as those electrons move through the circuit, they're going to lose electric potential energy as it's converted to something else. So the entire point of electric circuits is to take electric potential energy and convert it to some other type of energy. Let's say that you're just trying to turn on a light. So in that case, your load is going to be a light bulb of some kind, or an LED, or something like that. The symbol for just general load would be something like this. Okay, this represents a resistor. A resistor resists current flow. Now, some resistors are a load themselves. So in order to light a light bulb, you've got to put a light bulb in the circuit and it's got a filament. Let's just talk about an incandescent bulb to start off with because they're the simplest. Electricity will flow through that tungsten filament and the tungsten filament starts to heat up as the electricity flows through it. And when tungsten heats up, it glows. And that's why you get a light bulb emitting light. Most of that electric potential energy that is being used up in that light bulb is actually being converted to heat, which is why there's a big push to replace all incandescent bulbs with LED bulbs, because LED bulbs don't produce as much heat. They're much more efficient. They produce light using much less electricity than tungsten filament bulbs do. So tungsten filament bulbs are resistors. They resist current flow because they're using up that electric potential energy and converting it to heat energy and light. Okay? There are also resistors that are meant only to reduce the current flow before the current reaches another component in the circuit. So if you look at your phone, it has a whole bunch of different pieces that use up electric potential energy in different ways. So you have a speaker in your phone, you have a screen and it emits light, you have a microphone, you have all sorts of ways that electric potential energy is used up, and they all need different amounts of current to operate them. And so you don't want the full amount of your battery's current going through every component because not every component can actually deal with that much current, and so you will damage them. And so you'll have resistors in different parts of your phone circuit so that the correct amount of current flows through them. So resistors can be a load where they themselves actually take electric potential energy and convert it to some other useful type of energy, or they can just reduce the amount of current, which really they're converting it to heat, they can reduce the amount of current before another useful component. Okay, so that's the load. The load converts electric potential energy to some other type of energy. Now, if you're following along in the notes, there's also this section about resistor color coding. We're not going to worry too much about that part, but I do want to show you how it works. So here are some resistors. This is what they look like. Not all resistors. There's different classes of resistors that all look different. But this type of resistor uses colored bands to show what resistance they are, which is helpful if you're building your own circuit. You should probably know what the resistors are when you're putting them in. Okay, and so they have 4 colored bands. Let's look at this one, for instance. Yellow, purple, black, gold. Okay, each of those just corresponds to a number. And then that number may be some sort of scientific notation, and it may be a tolerance as well. So yellow, purple, black, gold is what we're looking at. Now if we look at this chart, yellow, purple, black, gold. So first of all, 4 is our first number, 7 is our second number, black is 0, and then gold apparently is -1. What could that possibly mean? Well, the numbers actually have different functions. So the first 2 numbers tell you what the resistance is going to be, just the digits. The third band tells you scientific notation. It tells you where to put the decimal place. And then the last band tells you what the tolerance is, or the error. So when you're manufacturing resistors, you can manufacture them to different tolerances. And so you may have a resistor with a 10% tolerance. You may have a resistor with a 5% tolerance. Those are the most common ones. And then you can get less tolerances as well. It's just that they are more expensive and more precise for certain purposes. So our yellow, purple, black, gold one would be 47 times 10 to the power of 0. 10 to the power of 0 is 1. So 47 times 1 would just be 47 ohms. Resistance is measured in ohms. And then our last gold band, it says that we have an error of 5%. Okay, let's look at one more. I think this is brown. Brown, green, red, gold. Brown, green, red, gold. So brown is 1, green is 5, 15, red is 2 times 10 to the power of 2. So 1, 5 times 10 to the power of 2. So that would be 1500 ohms. And then our gold band also gives us an error of 5%.